In this video, we're going to be having a look at the magnetic properties of materials and how magnetic fields within various different materials actually change because of the materials. Now, this will be very similar to the part of the syllabus that I've done on dielectrics, and there is actually a lot of crossover between the physics of dielectric materials and the physics of magnetic materials. And just like with lots of parts of magnetism, everything is similar but not quite the same. So let's go ahead and jump right into magnetic properties within materials. Now, to start with, we're actually going to go back to what we actually talked about at the very end of last video. And this was a coil or a loop of wire that was kind of square, just for convenience. And it was in a magnetic field, B, right here. So this is an externally applied magnetic field, and we had a loop of wire. And what we said was that if we were to somehow spin this loop on this axis right here, in the presence of a magnetic field, what you'd actually find is there would be a current generated, an induced current generated within the wire. And this is what was known as an induced EMF, and this was all governed by Maxwell's third equation. And what we're going to do is we're going to take a similar situation to this, but much like the solenoid, we're actually going to reverse what's going on. And rather than spinning a loop in the presence of a magnetic field, what we're actually going to do is we're actually going to apply a current first through the wire right here. So we have a current flowing within this wire, and it's, hooked up to some kind of power supply right here. Now, similar to the previous configuration, we're actually going to apply a magnetic field. But this time, we're actually going to apply this magnetic field in this direction right here, in the horizontal axis. So what's going to happen to this configuration? Well, we have a current flowing. This will be at right angles to the magnetic field, but it's only going to be on this side and this side right here. As we can see on this side of the loop, the current is actually directly opposite the direction of the magnetic field. And whenever we have currents that are parallel or anti-parallel, for that matter, to magnetic fields, then of course we get no force. It has to be at right angles. But it's safe to say that on this side right here and this side right here, there will be a force on the wire. So what direction is this force going to be? Well, it turns out if you apply the left-hand rule to both sides of the wire, then you find that there is an upwards force on this side of the wire and a downwards force on this side of the wire, because of course the current is in different directions on either side of the wire. And so what's this going to produce? Well, if we have an upwards force on this side and a downwards force on this side, then this coil of wire will start spinning. There will be a torque on this coil of wire, and that will cause it to spin. So essentially, this is kind of the reverse of what we had in the last video. Whereas before we were spinning it, and that was inducing a current, and this time we have a current and a magnetic field, and that is causing it to spin right here. And the way in which we talk about this physically is that we say that there is a torque, which we often give the symbol tau, which is a vector right here. So I'm going to try and see if I can calculate what this torque is, given we know the relationship between force, field, and current. And to do that, I'm actually just going to draw this loop slightly differently. So I'm actually going to draw it as if we were kind of facing it dead on. So technically this side would be the same as this side, but obviously we can't see the other two sides. And we said that there was going to be a force in this direction from that side and a force in this direction from that side. And when we're talking about things that are spinning, or something which has a pivot point right here, is that we can balance the moments around the pivot point. So as you can see, we have two moments. We have one from this side and one from this side. So the total torque is given by the sum of the individual moments, which obviously there's one on this side and there's one on this side. And the moment is of course the force times the distance away from the pivot point right here. We'll just call this D for now. So there's going to be one on each side. So what is the individual force on either side of the wire? Well, we know that the force of a current acting on a current carrying wire in a magnetic field is given by BIL times the sine of theta, right here, where L is the stretch of wire that is in the magnetic field. But what is our perpendicular distance away from the center of rotation? Well, if this entire side of the coil is of a width W, we'll just call it W for now, then the distance from here to here is just going to be W over 2 right here. So we say that the moment on the left is going to be equal to BIL times W over 2 times sine of theta. So that's one of them. But of course, the one on the right is going to be exactly the same, but in the opposite direction. But of course, it's contributing to the same kind of clockwise rotation right here. It's actually going to add to the amount of rotation that we're going to get, the amount of torque we're going to get. So essentially this just adds, we just add the same thing on again for the moment that's on the right. So we get another BIL W over 2 times sine theta. And so this will just add to BIL W times the sine of theta. That is the magnitude of our torque right here. But of course, L times W is simply equal to the area, our total surface area of the coil right here. So we can put this as being equal to BI times the surface area times the sine of theta. And that is the magnitude of our torque right there. But of course, we know that torque is a vector quantity, and so we kind of need to convert this equation into a vector equation so that we can kind of compare it with all the other quantities right here. And so we need to go ahead and identify which of these terms are vectors right here, which of these have a kind of directional dependence. Now we know that B is a vector, our magnetic field, and we also know that we can express the surface area, S, as being a vector as being equal to the magnitude multiplied by the normal of the surface area. And so we know that tau is going to be some kind of product between B and S right here, because of course current is simply just a scalar. And we have this sine theta, and this should give us a bit of a hint as to what kind of vector product we want to convert it to. And of course, whenever we see sine theta, that generally screams cross product, because of course if it was cos theta, that would imply that it's a dot product. But since it's a sine theta, we know that we're going to get the maximum when it's at 90 degrees, and that is true for the cross product. So as a vector equation, we can write that the torque is equal to the current, which is of course a scalar, and we say that it is the surface area cross-producted with our magnetic field. And that in keeps with the right-hand rule. It's that way around. Now, this term right here, we actually give a special name. The product of the current multiplied by the surface area is given the name of the magnetic dipole moment. And we normally give the symbol M. We sometimes give it mu, but I've seen M a little bit more commonly. And so we define this as being equal to the product of the current times the surface area right here. Or as an integral form, you can put this as an integral over a surface, just like that. So this would be some kind of surface integral if, say, we have something a little bit more complicated right there. And so going back to our loop, we find that the magnetic dipole moment right here, this M, is simply equal to the product of the current that's flowing multiplied by the surface area right here. So it's proportional to two things. And since, of course, the dipole moment is in the same direction as the surface normal vector, then it essentially points upwards right here. If our current's circulating around in that direction right here, our magnetic dipole moment points upwards. And this would be true of any kind of geometry. It doesn't have to be a rectangular coil. Even if we had a circle loop like this, and we had a current flowing around this loop, then our magnetic dipole moment would be pointing upwards, much like this, right here. So that's generally how magnetic dipole moments are defined. It's the product of the current times the surface area. And this is analogous to the electric dipole moment, P, which we defined as being equal to the charge, the electric charge, multiplied by the distance of the dipole, where of course the distance runs from the negative end to the positive end. And this is very, very similar. So instead of having a distance, as in the case with an electric dipole, we have an area, such as in the case with a magnetic dipole. And so whereas an electric dipole, you'd simply have a negative end and a positive end, much like this, a magnetic dipole is more of a orbiting current like this. So it's more of a little loop right here. And so whenever we have any kind of charge that's orbiting around a center right here, so any kind of charge that's circulating, then we know we have a magnetic dipole. And of course, we know of a system which has a lot of these magnetic dipoles. These are atoms. Of course, atoms just consist of a nucleus right here, and it has lots of electrons, at least on a classical level, just orbiting around the nucleus, much like this. And so this, because it has orbital angular momentum, the electron has orbital angular momentum, then it therefore has a magnetic dipole moment. So there is in fact an intrinsic relationship between the angular momentum and the magnetic dipole moment of an atom. And we're actually going to come on to talk a little bit more about that later down the line. But first of all, I want to introduce a few more quantities that you'll see a lot in electromagnetism that are very similar to the quantities I introduced in dielectrics, but this is going to be for magnetics. Now, say we have a massive system right here. We're going to draw some kind of like a solid or just any kind of system. And of course, the system is going to be full of atoms right here. And of course, I said that these atoms, because they are electrons orbiting around a nucleus, they are going to contain lots of magnetic dipole moments. So rather than just one magnetic dipole moment, we have a whole array of magnetic dipole moments all within the system right here. So this could be a solid or a liquid, but any essentially system of atoms will have a magnetic dipole moment. And we actually define what's known as the magnetization, which is capital M right here, as being equal to the derivative of the magnetic dipole moment with respect to volume right here. So this is technically the magnetic dipole moments per unit volume. Or equivalently, we can express this as N, where N is the particle density, multiplied by M right here, the magnetic dipole moment. And this is what's known as the magnetization of a material. Now, if we send a magnetic field through this material, so now we're talking about an externally applied magnetic field that we're going to send through this material. And it's going to be in this kind of direction right here. So it's going to be going into the solid right here. Then what's going to happen? Well, we have an external magnetic field, but this is of course going to interact with the magnetic field that is produced as a result of this circulating current right here. So what we can do is we can write that the total magnetic field that is experienced within the material is equal to the externally applied magnetic field plus an additional magnetic field, which is the induced magnetic field as a result of all of these atoms which possess a dipole moment causing an extra magnetic field to be produced right here. But we know that any magnetic fields that arise from the magnetic dipoles in the solid are of course characterized by a magnetization M right here. So we say that the induced magnetic field is the same as the magnetization M. And to keep the units correct, we actually multiply by mu naught, which is the permeability of free space right here. So we can say that the total B field right here is equal to the external B field plus mu naught times M right here. So let's go ahead and rearrange for the external B field right here. So we get that the B external is equal to B minus mu naught m right here. And we actually define this external B field to be a different quantity right here. And we actually define this to be mu naught times this quantity h right here. Now, many of you guys might have seen the quantity h before. It's actually quite commonly used, and it's slightly different to B right here. It's often given the same name of magnetic field, but I'm actually going to be referring to it as the magnetic intensity. So this h right here is the magnetic intensity. And this is essentially the magnetic field that is independent of any kind of material. So this is very, very similar to the relationship of D is equal to epsilon naught E plus P right here, back when we're considering electric materials or dielectric materials. This D right here was independent of the field applied, and that is very, very similar to this H field right here. This is the independent of material quantity, and of course this E of course is analogous to B right here. This is just the total electrical magnetic field observed, and of course the polarisation P is very, very similar to the magnetisation M. Both are defined in terms of dipole moments per unit volume. So we have a very analogous relationship to this equation right here. But of course, it's slightly different. So if we rearrange this equation for B right here, we get that B is equal to mu naught into H plus M right here. And this is actually slightly different to this relationship right here, because of course, what we said was that the polarization in an electric material actually produced a field that counteracted from the externally applied electric field. And D was the kind of like electric displacement vector, which is kind of what would have been there if there had been no electric field. But of course, something slightly different is going on here, because of course the magnetization actually adds to the total amount of magnetic field that is experienced within the material. So you not only do you have the magnetic field that's externally applied, which is quantified by this H term right here, but added to that you have this magnetization, which is produced by the little swirling dipole moments within the material to produce an even stronger magnetic field B right here. So yet again, it is very similar, but just a little bit different to electric fields right here. Now, if we take the situation in which we don't have a magnetic material, so we just have a vacuum in this case, then of course the magnetization is simply equal to 0. So what's going to happen in that situation? Well, we know that the B field right here, if M is 0, then B is just going to be equal to mu naught times H right here. And this is very similar to D equals epsilon naught E right here. So, and that is the case when there is no dielectric material and you just have a vacuum. This is the case when there is no magnetic material and you just have a vacuum. So that is the vacuum case right here. But in a magnetic material, we actually say that B, rather than being equal to mu naught times H, which is the permeability of free space, we actually just define the permeability anywhere as being the proportionality relationship between B and H right here. So this mu right here is any kind of general permeability right here. But of course we can set this equal to mu naught H plus M right here. And so what we can say is that this mu is equal to mu naught multiplied by some kind of dimensionless scaling factor, which we're just going to call the relative permeability mu r right here. So if we substitute this in, we get mu naught mu r H is equal to mu naught into H plus M right here. So the mu naughts are going to cancel, and if we rearrange this equation, we're going to get mu r H minus H is equal to M, the magnetization right here. And factoring this out, we're going to get mu r minus 1 in brackets times H is equal to M. And similar to the electric case, we can define the susceptibility, which we give the symbol chi, and this is the magnetic susceptibility, as being equal to the permeability, the relative permeability, minus 1 right here. And so from that, we then get the result that the magnetization is equal to our magnetic susceptibility times the magnetic intensity right here. So this is our result for magnetic materials, and it basically relates the amount of magnetization you get in response to a purely external electric field, because remember, H is purely material independent, and so this relates the amount of magnetization you get to H. And of course, this chi could depend upon lots of other different factors, so what you actually get for the expression of chi could be very, very different, but this is how they are generally related for an isotropic material. If it's anisotropic material, then it turns way more complicated and this actually becomes a matrix. But for now, it's just going to be a scalar. So M, the magnetization, is equal to the magnetic susceptibility multiplied by the magnetic intensity H right here. So this is actually going to change Ampere's law quite a bit because, of course, Ampere's law basically said that if you have a certain amount of current flowing, you get a magnetic field. And that was given by the equation of curl B is equal to mu naught J right here. This is going to change if there is a material present. And so say if we have some kind of current carrying wire right here, and we have our normal current as we did before, but around this current carrying wire, this isn't a vacuum anymore. This is going to be some kind of magnetic material. So I'll just color this in green. And if we were to construct some kind of surface right here, which is going to try and encapsulate all the current, not only are you going to have the current from the wire penetrate this surface, but you're also going to have these extra currents that are formed within the material. And so you actually have to add on an additional term to this equation right here. So the way in which you modify it is you say that curl B is equal to mu naught J as before, but you also get an additional mu naught J, and this is going to be the current density that arises from the material. So there's going to be extra current that you have to include that's flowing through this surface right here. And you actually define Jm as being equal to the curl of the magnetization vector right here. So if you have a magnetization and you take the curl of it, and then you get the currents that arise as a result of the atoms having an intrinsic dipole moment. And this is very similar to how if you were to take the divergence of the polarization vector, you actually get the bound charge, or minus the bound charge in a dielectric right here. So let's go ahead and substitute that into this equation right here. So we're going to have curl of B is equal to mu naught J, as we had before, plus mu naught Jm, but we said Jm is simply the curl of the magnetization vector right here. And so I'm going to subtract this right-hand term from both sides. So I'm going to get curl B minus mu naught curl M is equal to mu naught J right here. And you can actually factor this curl in like this. So we get that the curl of B minus mu naught M is equal to mu naught J right here. And this term right here, if we go back to our relationship that B equals mu naught H plus M, you get that this term in the brackets right here is simply mu naught H. So we can substitute this in and say that curl of mu naught H is equal to mu naught J. Of course, the mu naught's going to cancel, and so we get that the curl of the magnetic intensity is equal to J right here. And this is essentially Ampere's law within a material. So This is very similar to how Gauss's law in a material is modified due to the presence of there being a dielectric. And in a material, in an electric material, you have the divergence of the electric displacement vector is simply equal to free charge in the material. And so if you take the curl of H, you get the free current that's flowing, which is just the current that's flowing as a result of the wire, not the current that's arising due to the magnetic material. So there we go. That was an introduction to the magnetic properties of materials. And from this, you actually find that there are in fact 3 different types of magnetism. There is diamagnetism, paramagnetism, and ferromagnetism. Now, we have actually covered both paramagnetism and ferromagnetism on this channel already, and we did this using statistical physics. But we haven't actually covered diamagnetism on this channel yet, and so that will be the content for the next video on this series, in which we are going to be considering what diamagnetism is and how it applies to certain types of magnetic material. So, hope that was really helpful, and see you guys in the next video.